Hi, I'm Seth Margolis, an applications engineer here at Stratasys. I'll be discussing the use of fused deposition modeling, or FDM for short, with end-of-arm tools for robotics and automation. An end-of-arm tool can be thought of as the hand on the end of a robot. Essentially, the purpose is to repetitively pick up and move objects as part of a manufacturing process, quickly and efficiently, without fail. Traditionally, an end-of-arm tool is an assembly of several to dozens of individually sourced components. Often, a majority of these components are metal, which are heavy, need to be machined to size, and fastened or welded together. Costs can add up quickly between sourcing and shipping parts, machining and machinist time, plus assembly labor and any needed fixturing. Ultimately, they will all need to be fastened or welded together. This all takes time. Frequently, this can take weeks to months. If a third party is making the end-of-arm tool, more time is likely necessary. Another huge consideration with end-of-arm tools is the total payload. Any given robot will have a specified payload limit. The higher the payload limit, the more expensive the robot. Furthermore, the heavier payload limits attributed to a traditional end-of-arm tool will often mean slower cycle times and therefore less throughput. Printing with the FDM Nylon 12 carbon fiber material is a great alternative for many of the traditionally heavier metal components in an end-of-arm tool. The chopped carbon fiber lends high stiffness to the printed parts, which helps prevent the tool from deflecting when in use. There is also an inherent weight reduction when converting a tool from aluminum or steel to polymer, while maintaining a high strength-to-weight ratio. Additionally, the additive process allows us to create honeycomb infills with rigid walls, further reducing weight. This allows an engineer to print solid where necessary for additional strength, but reduce material where it is not needed. It's common to see weight reductions of 30 to 50% when comparing an FDM Nylon 12 CF tool to a traditional metal tool. A traditional tool can take weeks to months to acquire and use. An FDM tool can print in hours to days, depending on size. And once the file is sent to the printer and is started, the printing operation is almost entirely hands-off. Additively manufactured end-of-arm tools can be 25 to 50% less expensive than traditional end-of-arm tools once factors like materials, labor, fixturing, and shipping are all calculated. If your team has engineers familiar with CAD, they already have the knowledge to design end-of-arm tools. Because of the design freedom 3D printing allows, you can design and integrate functionality in the most efficient way possible. Using threaded inserts, such as heat set and helical inserts, additively manufactured tools can interface with other important hardware as required. Just size the holes in CAD to the insert's specified diameter, and after printing, the inserts can be installed just like in any other plastic. To get started with design for additive manufacturing, or DFAM, on an end-of-arm tool, first consider any critical touch points and attachment interfaces. Also consider the space between them. What is free space for creating the tool? What area is off limits to avoid interference with the function of the robot or tool? Use the answers to guide you as you begin to connect the key features of your tool together to become a solid body. One way you might do this is by starting with the original CAD of the traditional end-of-arm tool and drawing your new DFAM tool right over it. This way, you can convert any critical holes and features directly from the previous tool. Make sure to consider where threaded inserts and other inserts will be necessary, determine the inserts to be used, and make sure to properly plan for installation. This will likely include changing hole diameters for proper reception of these inserts. Also consider what additional functionality can be integrated into the additively manufactured end-of-arm tool. If it's a cobot, would extending the side covers protect an operator from pitch points? If there are tool changes on the robot, would locating features help decrease the time for these changes? Remember, complexity doesn't cost extra with additive manufacturing. Conversely, not everything on the end-of-arm tool necessarily needs to be printed. If there are some components that are inexpensive, readily available, or don't contribute to payload significantly, they may work great with the end-of-arm tool to create a powerful hybrid tool. Make sure to include fillets and chamfers rather than sharp corners for ultimate strength. Include self-supporting angles where possible to reduce support material consumption and print time. FDM Nylon 12 CF is a great material choice due to its strength to weight ratio, stiffness, and compatibility with Stratasys soluble support. To ensure parts are handled without damaging them, consider printing complex touch points in a non-marring material, such as FDM Nylon 12 unfilled. With FDM, we can project complex surfaces onto these touch points to help with a steady grasp. While Stratasys has multiple 3D printers with large build volumes, if your tool exceeds these dimensions, it is common to section parts into multiple smaller components and combine them through several means. I would recommend designing in joints that will help with locating the sections as well as provide mechanical strength. Depending on requirements, epoxies, fastening hardware, or both can be used to ensure a strong connection. Depending on the size of your end-of-arm tool, a build will print as fast as overnight to a couple of days in most cases. Keep in mind, the sparse infill we can apply with FDM not only reduces weight, but also reduces total print time. Factor in any post-processing steps like support removal and hardware installation, and your end-of-arm tool is ready significantly faster than traditional methods would allow for. By using advanced composite materials, you can produce complex end-of-arm tools in-house with the proper accuracy and increased functionality necessary to improve existing processes. To learn more, contact your Stratasys representative or visit stratasys.com. Thanks for watching.